So let me start out by asking a question. Have you ever made a mistake in your tech program? Yeah, me too. So that's why I had the bright idea that I would create a tool which would tell you about all the mistakes in your tech program, and then you could just go ahead and fix them. So I researched the literature, and unfortunately it turns out that this isn't really possible. So I would like to thank you for your attention, and I will take questions from the audience. So I'm just kidding. There are things that we can do. In general, there are two broad classes of approaches which we can take. We are all familiar with the second one, the dynamic analysis, where you just take your code, you compile it, and if it compiles, it works, right? Well, not always. Not all bugs will crash your program. Some bugs will just make it behave differently than what you expected. But that's no problem. You can just write a couple of tests which specify what should happen. And if your program does something different, then there's a bug, right? But that's still a lot of work. You still have to write these tests. And it would be nice if you didn't need to do this. So that's what the first one is all about, static analysis, which basically means that you don't execute the code, you just read it, or your tool reads it, and it tries to determine if there are any mistakes in it just by looking at it. Now, here is where the theory comes into question. The Rice's theorem tells us that this can't really be done for arbitrary Turing machine programs, but fortunately, modern programming languages are not Turing machines. I mean, they are Turing complete, but the programs are not the Turing machine tapes. There are extra information which restrict the programmer and which help guess the programmer's intent, and which allow us to find out if the programmer made a mistake or not. For example, in most programming languages, you differentiate between data, which are represented by variables, and functions, and code, which is represented by functions. So if the programmer defines a variable and then tries to call the variable instead of calling the function, then you can immediately see that this is an error, and you can report it without executing the code, right? Or most modern programming languages have a type system. So for example, if you declare a number variable and then you try to assign a text to it, then that's obviously a mistake, and you can detect it without ever running the code, right? So that's the idea behind static analysis. The type of errors static analysis reports are broader. Unlike tests, which really target the specifics of your program, static analysis tries to determine if there is some general error supported by the programming language in your code. So it's sort of, you don't need to write any tests, but it's more general. It's sort of like a first line of defense, like a very general code review, which tells you if there are any general errors, and if there are no general errors, then you may run your test suite to find out if there are any more interesting bugs which are really specific to your application, which cannot be determined just by looking at the syntax of your code. So the issue with applying static analysis to TeX is that, unlike many modern programming languages, TeX is really quite close to some sort of a machine code. Its syntax is very minimal. So for example, if you define a macro, it's not clear whether it's a function or a variable or what's its type. There could be anything in there. right? So it's very difficult to know what the user intended just by reading this. Also, TUG is very dynamic, which is nice if you just want to hack together a couple of macros in your article. It's very dynamic. You can even change the categories on the individual characters. So try to statically analyze this, right? I mean, at the end of the line, this looks nothing like what you would expect in a TUG code, and definitely it's not something that you could highlight a syntax in using an open type font, I suppose. It looks more like an XML. So that's an issue which severely limits what can be done using the static analysis. What we would like is some restricted, more annotated form of TUG, which would allow us to glean the programmer's intent. So thankfully, we don't need to imagine it. It already exists. It was developed by the LaTeX team to make the LaTeX kernel easier to maintain. It's a restricted and richly annotated subset of TUG, which currently makes up more than 10% of all TUG code in the TUG Live distribution. So here's an example. For example, here's a definition of a function. You can see it's a public function because there are no underscores before the name. You can also see that there are 4 letters after the colon, which signifies that it has 4 arguments. And below it, you can see a definition of a local variable of a type int. And all this extra information, it helps the programmer who's reading it to see at a glance what's the intention, but it also helps an automated tool who can say, okay, you've defined an integer, but now you're assigning a text to it, so maybe you've made a mistake, right? So just like with the modern programming languages, all this extra information can be used to do some automated checks. So I developed a program called expl3, which is a static analyzer of expl3 programs. It all started in April last year, where I came up with the idea that this might actually be possible. And I started cold mailing some of the LaTeX developers with some ideas. So this was annoying to them. So instead, I just started writing blog posts. I wrote a bunch. And then in September, I compiled all these blog posts into a project proposal to the TUG Development Fund. I sent it out, and the TUG Development Fund graciously decided to fund this project. And since September, I have been developing this tool. Here you can see the mascot of the project, which is Platy, an underwater detective, which helps you discover all the issues underneath the surface of your code. It was ideated by Paulo Cerida from the Island of TUG organization. Thanks, Paulo. It was drawn by Greg from Quick Cartoons and licensed under the CC BI, so Creative Commons Share Alike with Attribution license, which means that you can use this artwork in your projects, in your presentations, provided that you give attribution to the artist. You can find all the artwork commissioned for the project at this address. And the Expltools tool is bundled into a bundle called Expltools, which you can find on C10. Currently, Expltools is the only program that is part of this bundle, but I envision that there will be several different tools which would be helpful to Expl programmers. Currently, there's only one. If you'd like to try the program, you should have a look at the README file, which contains links to the articles, examples of how you might use the different interfaces exposed by the tool, the command line interface, the Lua interface, and so on. So go and have a look if you're interested. Yeah, that's basically it for the introduction. So here's the outline of the talk. First, in the first two sections, I would like to discuss with you how it works. Then, in the fourth section, I would like to show you how to use the program. Then a quick experiment to determine does it work or does it not work. And then in the end, I would like to discuss some ideas about how to make the tool better before concluding. So first, how does it work? So here you have some example LaTeX document without syntax highlighting. Sorry. Yeah, that's true. So I mean, you can take this document and compile it, and you will get this nice output. It works clearly. There are no errors, but there's a lot going on, which you can't tell just by compiling the document. But for this, you need to go under the water, because by compiling it, you see just the literal tip of the iceberg. So if you use expl-check, first the code is split up into expl3 parts, because in the original document, there are different parts. Not all of it is expl3 code. Some of it is just LaTeX. So first, the expl3 parts are extracted, and an error is reported for an extra separator, which was unnecessary on line 15 of the code. So that's sort of the first warning that the tool would give you. Then in the second step, these parts are tokenized according to the rules of TUG. So you get control sequence tokens, character tokens, and so on. In this step, several more warnings are reported, which report the missing white spaces here and here. It's customary, and it's actually defined in the expl3 documentation, to use white spaces around braces. So if you miss them, the tool will give you a couple of style warnings, which you can disable, but which help you ensure that your code looks nice. And we need to do it at this stage, because after this, the spaces produce no tokens in expl3. So after tokenizing, the spaces are not there. So this is really the stage where we need to report these errors, because afterwards we just lose this information and we only work with these tokens. So next up, we merge these tokens into individual expl3 calls. We don't try to understand what these calls mean. We just get a list of calls, including arguments. Here we get another warning, because at this point we are parsing the arguments, and we see that there are missing braces around this first argument of this example function. So you get a warning about this, that it's better to surround n-type or lowercase n-type arguments with braces. In the next step, called the semantic analysis, you actually try to determine what these individual calls mean. So you see that we are reserving a stream and opening a file for writing, but we don't actually use this stream anywhere, and we don't close it even. So we get a warning for that. Then we define a function. The definition of the function is also parsed, so you get the body of the function and all the calls and statements within this function. Then we generate a bunch of variants. The first variant is never used in the code, so we generate a warning for that. And And then we call two user functions. And in the last step, we take these statements and we merge them into blocks of code that we can understand, which are on the same level, so not nested within a function definition. And then we build a graph which says how the code actually flows, how the control actually flows through the program, which allows us to determine that we actually never use this stream and allows us to report this warning. So that's basically what happens under the hood. Conceptually, so let's now take a look at how it's actually implemented. So first, here is the package diagram, which illustrates the structure and organization of the Lua modules that make up the linter. Starting from the top, first you have this analysis package, which performs the different processing steps, which you saw in the figure that we just discussed. Then we have an evaluation package, which computes summary statistics about the individual files that you're processing. Then there is the config package, which manages user configuration files. The format package, which produces command line output. The issues package, which registers the individual warnings for errors that the tool sees in your code. The CLI package, which implements the command line interface. And then this miscellaneous package, which implements low-level data types and also some helper functions for the rest of the tool. So this is a different view. This is a component diagram which shows the interactions between the file system, the Lua modules, and the users. So first, you have some expl3 file on the file system, which is consumed by the analysis package that does the individual processing steps. The analysis package registers all the issues that it can find with the issues package. Both the issues package and the analysis package are configured by config files, by command line arguments, which are provided by the config package. When the results are finished, they are evaluated by the evaluation package, and the results are consumed by this, and also the warnings and errors are consumed by this central command line interface package. The results are formatted and then passed either by people using the human readable output or to other tools using machine readable output. And here is yet another view. Now I'm zooming in on the analysis results. This is like the internal representation of an expl3 file by the analysis package. This is what we actually see when we analyze the file. So first, the pre-processing step splits out the file into individual expl3 parts. Then during the lexical analysis, each part is tokenized into a bunch of tokens and also tag groupings, which indicate where the arguments may begin or end. Then the syntax analysis determines calls and their arguments. Then the semantic analysis actually determines the meaning of these calls and classifies them as statements. For function definitions, the arguments are actually understood as the replacement text, and there is sort of backtracking where you invoke the syntax analysis and detect calls and arguments and statements inside this replacement text as well. And then at the end, you take all these segments, which are either the parts or the replacement text from a function definition, and you build up chunks of well-understood statements, and you build the flow graph, which tells you how the control flows through the program. So that's basically it. So this was a description of how it works, and now let's see how we can use it. As one example, Oliver Kopp and me produced this website, which uses the machine-readable output of expl to produce a list of warnings and errors of all packages in TechLive and displays them. If you click the individual links, it actually shows you a text editor. And in the text editor, you can see all the warnings and errors highlighted directly in your web browser. So this is nice because each time I develop a version, I take a look at this, and either I see a lot of bogus warnings and errors, so I know that my tool is wrong, or I can actually see some good warnings and errors, and then I can go and talk to the developers and maintainers and say, hey, this is a link that shows you all the errors in your package. Please go fix it. So there weren't many actual errors found yet, but I have had a lot of interactions with developers already, and most of the issues that I've reported this way have already been fixed. Some of the packages have already decided to use this in their continuous integration pipelines, so they are using this continuously during their development, not just using this website. So that's one example. Here's another example. I created an example LaTeX document which lists almost all expl3 functions which are defined in all packages in TechLive. And then it compiles this 3,000 pages long LaTeX document. You have an index of functions, you have an index of files. So if you're a developer and you're developing a package that uses expl3, you should find yourself in this document. I'm not sure this is very practical. Ideally, I would like to have a website where you can search for expl3 symbols rather than like printing this out and searching through 3,000 pages. But it shows what can be done in principle. So that's a demo. And now let's see how well it works and how I plan to make it work even better in the future before concluding the talk. So here's an experiment. I used a recent release of TechLive, and I used expl to process all or most of the tech files in TechLive and print out the aggregate statistics produced by the evaluation module. So the files make up about 200 megabytes, so that's quite a lot. And about 12% of this, about 25 megabytes, were detected as expl3 code. Out of these 25 megabytes of expl3 code, 56% of tokens we just didn't understand. It's some type of statement. Maybe we detected it as call, but we didn't know how to classify it. We didn't know what that call means. So that just More than a half is we don't understand it right now, because as I'm going to tell you, we're still in the middle of implementation. So currently we support mostly just function definitions and not other calls of statements. 20% of these 12% of all tech code in TechLive are function definitions, so we can parse these, and also all the nested content within these function definitions. And then there are some 10% of tokens which are some other tokens which we weren't even able to form into calls. Those are just some sequences of tokens which we don't understand. And then there are some function variant definitions, very small percentage, and also some other tokens which are simple. That means that those are just letters and some text. The distinction is not really meaningful. So at this point, we can understand like 2 to 3% of all tech code in TechLive, which doesn't seem like much, but it's a start. At this point, 3 out of the 5 processing steps that I showed you are finished. So we can tokenize the code, we can parse out the calls, and that's it. We are currently in the middle of the classification phase, where we understand the different types of calls. Right now, we understand function definitions, but other types of statements, such as variable definitions and variable use, are not yet implemented. We are in the middle of it. There is a document listing all the warnings and errors which are planned for the final release. So we are, again, kind of in the middle of this document. So at this point, about 40% of these warnings and errors are actually reported by the tool, whereas the rest is just documented but not yet implemented. And here are some points of future work from our issue tracker. The first one supports serialization of analysis results. From the beginning, the tool was designed as a tool for reporting warnings and errors. Warnings and errors were like the main deliverable, the thing of interest. But as I was developing the tool, I became convinced that this is actually also a thing of interest, right? It would be very useful if the tool could actually export this into some format such as XML, so that other tools could actually ingest this and use it for indexing and other purposes. So that's one idea, that in addition to producing the list of issues, the warnings and errors, the tool should also be able to serialize this internal representation of these expl files. Because in fact, this is more general than the warnings and errors. You can determine most of the warnings and errors just from this internal representation and without access to the original file. So you could just produce this output, and then another tool could do what we do now, just determine the warnings and errors. We could even do it internally, right? We could first produce this representation, and then as a separate step, we could just report the errors. Currently, those are intertwined. We produce this representation incrementally, and as we do it, we actually register the issues. But it could be done sequentially to simplify the code. So that's first idea. Another idea is to support package imports, so use package or the primitive input command. Currently, if your package uses some functions defined by some other package, and those functions are not the standard functions defined by LaTeX, you will get an error saying that this function is undefined. You have to say in your config file, these prefixes are actually defined elsewhere. So this works, but it would be ideal if we could dynamically look for the other packages and just at least see what functions and variables are defined there, so that when they are used in the file that we're processing, we don't report them as errors. Also, in addition to the parts and replacement texts, it would be also nice to recognize true and false branches of conditional functions as their own segments so that we can analyze the code inside these. It would also be nice to support Unicode. You may be horrified to learn that we don't support Unicode yet. The tokenization part is just the standard TeX tokenization algorithm. It doesn't implement any of the Omega extensions, which again sounds horrible, but it actually works well in practice because we don't really care about the text. And not many people are crazy enough to use Unicode in the control sequences. So for the most part, we can live with this, but it would be nicer if we could actually support Unicode. And also, we would like to support .ins and .dtx files. Let me explain. .ins and .dtx files are common ways in which LaTeX packages are documented and distributed. The .dtx file is a documented TeX file, which contains the code of the documentation along with the code of the documented package. So it would be nice if Expl3 could actually read the documentation part of the DTX file and see if there are any errors, not in the package, but in the documentation itself. This is what would happen if you would pass the DTX file to Expl3. And it would also be nice if we could support .ins files, which are sort of like archive specifications. They specify how you can generate the actual files which are distributed in C10 and in TeXlive, how you can produce them from these DTX files. So it would be nice if Expl3 could just read these .ins files and construct sort of virtual files that would contain the correct content, similarly to how the docstrip package does it. So then in your continuous integration, you could just run Expl3 on the .ins files without actually generating your package, actually. But those are nice to haves. I mean, the DTX would be an actual improvement in functionality. For the .ins files, this is just a nice to have because you can always run TeX on the .ins file and produce the package files and check these. But it would be sort of nice if you didn't need to do this and if Expl3 could actually understand these .ins files itself. But it's not really a priority, just an idea, because if we supported this, we could also support different types of archives, such as zip archives and so on. So you could just pass in your package as a zip archive, and it would automatically go through all the package files inside the zip archive. This could be a nice usability improvement. It's not something that, it's not a missing functionality, it's just usability. So these are some ideas. We have more, but those are sort of the ones that I wished to highlight. So for conclusion, we can use static analysis to check programs without running them, but this is not usually done for TeX because TeX is a very low-level language which is difficult to parse. expl3 is rising in popularity. There is about 12% of code in TeXlive, which is out of all TeX code, which is written in expl3, and this programming language makes it much easier to do static analysis. Expl3 is an expl3 linter, which I developed as a part of a TeX development fund project. Expltools is a bundle which includes Expl3 and perhaps soon other tools that are intended to help expl3 programmers do their job more effectively. Current version implements about half of what was intended. So the estimation is that the full thing might be done somewhere around the beginning of the next year. I was planning to submit an article for the conference proceedings, but the idea is that it would all be done by this point. It's not yet done. So the article is not yet done either. If you look inside your conference proceedings, there is a link to a work in progress article, which you can take a look at. It's also about halfway done. I expect when the tool is done, the article will also be done, and then you will receive it in your tugboat, but of course you can take a look at the work-in-progress version right now if you'd like. So that's it from me. Thank you for your attention, and I'd be happy to receive questions.
Thank you for your talk. Are there any questions here?
Do you also seek collaboration with plugin creators like Techify Idea? Like they do also very much analysis about the LaTeX 2A format, but not LaTeX 3A.
So the question was whether this work could be integrated into an IDE. Is that it?
Yeah.
Yeah. Yeah, that's the idea. We currently export the standard error format. That's the machine readable part. So you can just plug it into your IDE. In the final article, I will have a demo that will show you how you can actually integrate this with Vim, Emacs, and other IDEs. Just by passing in the error output, it will highlight all the places where warnings and errors were detected. There's also it's also envisioned that you could use this tool as a language server. So it would actually tell you more things about your code, not just the warnings and errors, but also where the different functions are defined and so on, so that the IDE can actually get an idea of what kinds of functions are defined where and allow you to easily access them and so on. But this is just a work in progress. Currently, you can wrap the tool in a separate program, which will actually make it behave like a language server. But currently, it just reports warnings and error, no extra information.
Thank you.
Hi, you had said at the beginning that because of some theorem, the static analysis cannot completely do all the things that will be useful for us. But then you said that real programs will be having extra information when compared to a normal Turing machine tape. So what could be that extra information that you mentioned that would be useful?
Well, as I told you, right? I mean, modern programming languages, they are not really machine code. We are not coding in machine code. They are more like a recipe to build the final either binary or to be interpreted at runtime. So as I told you, like the distinction between variables and functions, the types of the variables, this is all information that you don't strictly need in an interpreted language, but it's all an extra information that you can use to see whether there is an error or not, right? It's some sort of redundancy. You could have a much simpler language, such as TeX, which doesn't have this information in there, which you cannot check. So in modern languages, there's a lot of these restrictions which try to prevent the programmer from making mistakes by making them explicitly type out what they wanted to do, even though the machine could do without this information.
It's like when compared to bytecode or something, maybe.
Sorry?
Maybe when compared to this binary form, the program has much more structure that we can utilize.
Yes, exactly.
Yeah, sure. One question, probably just because I didn't really look into the program recently, might be solved. But if you have a situation that you know that there will be warnings of a certain kind, I mean, I just look at what you report on the LaTeX 3 kernel, which is something like 2,500 messages of errors, of warnings. And the large one, is, for example, is that the kernel uses functions that say don't use, which is :D. Well, the kernel has to because it defines the other one. So it would be nice if there's a way statically in the file to say, shut up, this warning for this file is there. I mean, something that you can put as a comment at the top of a file.
Yeah, there is actually, if you look at the...
Okay, sorry, but it is nice to learn.
Yeah, there are comments. Similarly to when you use some Python linters, you can just write a text command which says, ignore this line, or you can write it at the top of your file.
Should do that. That looks better.
Just to add to Frank's comment, maybe we can, like, especially because the D argument type is defined for do not use, maybe we can search for the module name, and if the module is kernel, then you should not give this warning at all. That also can be a good idea.
Yeah, I mean, we have a special config file just for the expl3 issues website, where we like special case some packages because it's clear that some of the errors are not really errors, and the tool is not perfect at the moment, so there are predefined errors which are just silenced so that we don't get a lot of noise. But yeah, I mean, the expl3 kernel is not really the target code because it defines expl3, whereas the tool relies on the code being just the user of expl3. So there's a lot of it's nice to try it against the expl3 kernel, but the tool will never do a perfect job there.
So if there are no further questions, are there some online perhaps? If not, we could have a coffee.